And this, the first is boron family. Boron family. Okay. Now, in boron family, that is the group 30. So what are the elements in boron family? Do you guys remember? Yes, tell me. We have, first of all, obviously boron. नहीं याद है आप लोगों को. बैगन, आलू, aluminium.
बैगन आलू गाजर इन थैला.
Yes. Gallium. Then we have indium. And then we have thallium. We have boron, aluminium, gallium, indium, and thallium. So the atomic number of boron is 5, aluminium is 13, gallium is 31, indium is 31, 18, 49, and this is 81. Okay, now you guys can write the electronic configuration, yes or no, for all of them?
Yes, sir.
Okay, fine. So you'll write the electronic configuration here. Okay, I'm not going to write it here. So this is going to be your homework, the electronic configuration of boron, aluminium, gallium, indium, and thallium. Next, we can write some general things. Number first point regarding boron is that boron has two isotopes. Boron has two isotopes. One of them, it has atomic mass of 10 and it is 19%. The abundance is 19%. Then we have boron, which is 11, and the abundance of this boron is 81%. It is 81%. Okay. Next is aluminium. Okay. Aluminium, you can write aluminium is the third most abundant element found in Earth's crust. Okay, found in Earth's crust. Fine. Now we'll write about the physical properties. Electronic configuration, please याद से लिख लीजिए electronic configuration. Okay.
Yes, sir.
Then okay, fine. Next you will write the atomic radius, physical properties, and in that atomic radius. The physical properties.
Sir, could you show the second point again?
Yeah, sure. Acha, Imran, what about you? When are your examinations? Yes, Imran. Imran नहीं है क्या? Started. When did it start, Imran? Imran क्या start हो गया है? Yes, Imran, when did it start? Yesterday. First exam. When is chemistry then? When is your chemistry exam? You don't know? Where are you? 27th. Okay. आपकी एग्जाम चालू भी हो गया. Strange. And Khalid, you're done, right? Yes, Khalid.
Yes, sir. My screen is a bit lagging for me.
It is
For me.
lagging for you. Acha, acha, acha. Okay. So I can move, right? Physical properties. Now in physical properties, first of all, we'll write about the atomic radius. Okay, first of all, we'll write the atomic radius. Number one. Atomic radii. So the first point is that if I compare the ionic radii of group 13 elements and the group 2 elements, we can already say that the group 13 elements will be having smaller atomic radii. Okay, so please write number 1 point. Group 13 elements have smaller than group 2. Okay, in the corresponding period, in corresponding period. Why is that? It is because of the, if we increase the nuclear charge, now if I am going from 2 to 13, right? I'm going from 2 to 13. That means what I'm doing, I'm increasing the nuclear charge. Increase in atomic number leads to increase in nuclear charge without in the same, you can write in the same shell. In the same shell. Okay, in the same shell. We have already seen this, right? We have already seen this happening. If we move along a period, then what is going to happen? We will have a decrease in the atomic radius. Right, next point. On moving down the group, both atomic and ionic radii is expected to increase. Why? Due to addition of new shells. If the shell number is increasing, that means we are increasing the atomic radius. But there is an anomaly here. There's an anomaly here. So what is the anomaly here? In this case, the anomaly is that, but as we move from aluminium, it has the atomic radius of 143 picometer, to gallium. Gallium has the atomic radii that is of 135 picometer. As we move from aluminium to gallium, there is a slight decrease in atomic radii. Slight decrease in the atomic radii. Okay. Now, why is this happening? The first thing is that aluminium is 13. Aluminium is 13. What is the electronic configuration of aluminium? It will be having, tell me, neon, right? Neon is
yes,
10,
sir.
and then
3s2, 3p1.
3s2, 3p1. Okay. And if I compare this with gallium, which is 31, so here we'll be having argon. Yes or no? Argon, right?
Yes, sir.
Argon, and after that 4s2,
4s2, 3d1. No,
3d10, 3d10,
4p1.
4p1, right? In this case, you can see that we have the fourth shell here, and in this case, we have the third shell here. Now, this third shell, it is shielded by inner electrons, but this 4s electrons, but this fourth shell electron, these are shielded by only 3d10 electrons. Now, this d, as we know, as the d subshell, is ineffective. Okay, rather I should say, right? The d subshell has poor shielding effect. Poor shielding effect, and the highly increased nuclear charge is able to attract the outer electrons more effectively. And hence what we can say, hence atomic radii of aluminium is smaller than the atomic radii of aluminium is greater than the atomic radii of gallium. It is greater than the atomic radii of okay. So right here, the expected order of atomic and ionic radii was that the boron should be the smallest, followed by aluminium, gallium, indium, and thallium. But the actual is, you have boron, then we have gallium, then we have aluminium, and after aluminium, we have indium, which is approximately equal to thallium. Okay, just because this indium is 167, thallium is 170, so it is comparable. It is very comparable. Okay, but still you will follow this order: indium, and after that there is thallium. So there is a discrepancy only in aluminium and gallium. Now the reason for that is the D subshell, which is poor in shielding, and there is a high jump in the nuclear charge. So if you have a high jump in the nuclear charge, and if it is followed by a very good shielding effect, then there will be as expected. But since we have a very high jump in the effective nuclear charge, and the atomic radius, it is defined as the What is atomic radius? Atomic radius is the distance from the nucleus to the outermost electron, right? That means we are effectively talking about how much a particular proton or the nuclear charge can attract the electrons. If it can attract it easily, then it will be very small. If it cannot attract easily, that means it will be a very large atom. Write this down. Let me know if you're done. Then we will talk about ionization enthalpy. Done? Yes, Hamza, Hiba, Khalid, Salman. Done, guys?
Yes, sir.
No, sir.
No? Okay, Salman.
Done, sir.
Right, next, ionization enthalpy. In ionization enthalpy, we all know that if I compare the ionization enthalpy of the alkaline earth metal, that is the group 2, and the ionization enthalpy of group 13, there will be a decrease in ionization enthalpy. Okay, so write with me. Ionization enthalpy of group 13 is less than the ionization enthalpy of group 2, alkaline earth metals. Why? The reason is that the outermost electron in group 13 is in p subshell, but in group 2 is in s subshell. It is easier to remove electron from p subshell than s subshell. Hence, the ionization enthalpy of group 13 is less than ionization enthalpy of group 2. Done?
No, sir.
Okay, right. Yeah, let me know if you're done.
Done, sir.
Done. Okay. The next thing is that, okay, as you know, all will know that in group 13 element, the valency is 3, right? The valency is 3. The oxidation state will be plus because it has 3 valence electron, and if you remove 3, we can remove 3 valence electron. So we have a group 3 element let us say boron. And if I remove one electron from boron, it will be boron positive plus an electron. So this will be delta H1, I will say, ionization enthalpy 1. Then we have boron positive. If I remove one more electron from here, it will be boron 2 positive plus an electron, right? This let us call as delta H2. Then I can also have boron 2 positive, and I will remove one more electron. This will be boron 3 positive plus electron. Let us call this delta H3. So this is small, this is high. Okay, this is very high. Okay, this is very high. If I compare this, then I can say that delta H1, it is very, very small than delta H2 and delta H3. Delta H2 and delta H3. Okay. Now, what effect it is going to have on the reactivity? We will also discuss that now. But this is important that we have the ionization enthalpy. First ionization enthalpy is okay. First ionization enthalpy, it is very small. The second ionization enthalpy is very, very high, and the third ionization enthalpy is also very high. If I compare that to the first ionization enthalpy. Done, guys?
Done, sir.
Okay. Right here. Since the valence electron in p subshell is easily removed, but the valence electron in s subshell have very high ionization enthalpy, very high ionization enthalpy. These s subshell are also not available for bonding easily. For bonding easily. Okay. So this reluctance of s subshell, the reluctance of s subshell to take part in bond formation, to take part in bond formation, to take part in bond formation is called inert pair effect. It's known as inert pair effect. Okay, it's called inert pair effect. Write this down, then we will write the consequences of inert pair effect. Done.
Yes, sir.
Okay. Right, next. Since gallium is smaller than aluminium, hence ionization enthalpy of gallium is a bit higher than aluminium. Okay, so again, the expected order was of ionization enthalpy. Expected order was that the boron, it should have the highest, followed by aluminium, by gallium, indium, and then thallium we will not consider because thallium is a metal. Okay, thallium we will not consider because thallium, it is a metal. Okay, then we have the actual one. But if you want to write, you can write thallium after this only. Okay, but generally thallium is not compared. We'll have boron, which will be followed by gallium, followed by aluminium, indium, and then thallium. Wait a second, wait a second. Can you reverse this order also? Since thallium, it will be easier, yeah. Thallium will be easier. Right here, indium, thallium. Thallium is easier than indium. The explanation here it is a metal. And metal, it has a tendency to lose electron. Done, guys? Right, next, electronegativity. This was the second point. Third point is the electronegativity. So electronegativity of group 13 is more than group 2. Now, why? Due to increase in effective nuclear charge due to increase in effective nuclear charge. Then down the group, if we compare the electronegativity down the group, what is going to happen? It will decrease down the group. The electronegativity decreases from boron to aluminium, and then increases down the group. Due to poor shielding, poor shielding of D and F orbitals. Done, guys?
Done, sir.
Okay. So electronegativity is done. Write the next one, that is melting points and boiling points. Both melting point and boiling point. Both melting point and boiling point decreases as we move down the group. As we move down the group. Okay. Now, why is this happening? You have to here compare the forms of different molecules, different elements. We have boron. So boron, it is a covalent compound, right? It is non-metal, it is covalent. Non-metal, right? It is a non-metal and it is covalent. It is very hard. It is very hard, and it has a crystalline lattice type structure. That is why it is having very high melting point. Very high melting point. So non-metal. Then you have gallium. Next we have boron. Then we have Then we have aluminium. Aluminium. Then you have gallium. Then you have indium, and then we have thallium. Right. So all of these are soft metals. Okay. Now aluminium you have in your home also, right? Aluminium you have in your home also. A small dent also, it is what it if you exert a small force, it dents the aluminium. Gallium, it is so soft that it melts in our hands only. It will melt in our hands only. Okay. So these are soft metals. Boron is a non-metal and it has crystalline lattice type structure. That is why it has high melting point. It has network. It is network solid. Done. Done, guys.
Yes, sir. Done.
Right, next, the metallic character. Fifth point. Metallic character. Or we can also write electropositive character, electropositivity. Yes, electropositive character. Now, if you have very high ionization enthalpy, then we can say that these are less electropositive. These are less electropositive than group 2 elements, and that is why this will be having less metallic character. Less metallic character. Okay. Now, on moving down the group, the electropositive character. Increases. Okay, because you can see boron is what? It is a non-metal. Aluminium, gallium, thallium, indium, all of these are what? Metals. So you can say the same thing about metallic character also. It is less than group 2, but moving down the group, the metallic character starts to increase. The next is the oxidation state. This is going to be important. Okay, oxidation states of oxidation state. Done? Done, guys?
Yes, sir.
Yes, sir.
Okay. Now let us talk about the oxidation states. So we know that all of these, all group 13 elements show a maximum oxidation state of +3. They will show a maximum oxidation state of +3. Okay, but let us first of all talk about boron. So boron is small with very high ionization enthalpy. Okay, ionization enthalpy. Now, if I will add the first ionization enthalpy of boron, it is going to be very high. Very high ionization enthalpy, and the first 3 ionization enthalpy of boron is very high, is very high. Hence, it is not possible. Hence, it's not possible for boron hence it is not possible for boron to be in ion. That means if I am going to remove 3 electrons, it is not possible. Hence, it is not possible for boron to form ionic compounds. Okay, so boron forms it will form what? Covalent compounds. Okay, but as we move from boron to aluminium, we see that there is a considerable decrease in the first 3 ionization enthalpy. Okay, now after boron, all these aluminium, then you have gallium, and then indium, and then thallium. All of these, they will form the +3 oxidation state. Okay, they will form ionic compounds and be in +3 oxidation state. So after boron, aluminium, gallium, indium, and thallium all can form +3 oxidation states. Okay, why? This is due to poor shielding of DNF orbitals, DNF subshells or orbitals. And since they are poor shielding, what will happen? Due to poor shielding, what will happen? Due to poor shielding of DNF subshell, the stability of +3 oxidation state decreases down the group. Okay, that means if I will have aluminium, then I will have gallium, indium, and thallium. Okay, so aluminium, it does not have any S or any D. Gallium has D subshell. Indium also has D subshell, and thallium has D subshell and also F subshell. Okay, and also F subshell. Now for aluminium, it will be a bit difficult. Then for gallium, it will be more difficult because D subshell, it is what? It is poor shielding. Indium also, it has D subshell, it has poor shielding. Thallium, it has both D and F subshells, which means that thallium will be having very poor shielding, and we cannot remove electrons from the thallium. We cannot remove electrons from the thallium. Okay, that is why down the group, stability of +3 oxidation state decreases, and stability of +1 oxidation state increases. Write this down. Let me know if you're done. Okay, Iba is done. So Hamza, Khalid, Imran, and Salman. Okay, all of you are done. Okay, fine. So we will look at the chemical properties on Tuesday, on next Tuesday. Okay, we'll look at the